All right, so first of all, our makeup session will be next Wednesday, right? From 3:15 to 4:15. It's going to be recording and everything. So then you'll have 15 minutes break and start again. Okay. I could make an announcement on Canvas maybe with email sent to everybody. Yeah. All right, so last time we've seen that every inner product space, so vector space equipped with an inner product, finite dimensional, admits an orthonormal basis. And we've seen that this is possible through that procedure, which is called the Gram-Schmidt, which takes any linearly independent set and transforms it first into an orthogonal set with the same span. And then once you have an orthogonal set, you can easily make it into an orthonormal set, right, by normalizing every vector in there. So the last thing that we proved last time was about this idea of splitting a vector y of an inner product space V into a unique sum between a vector u in a finite dimensional subspace W of V and a vector z, which is in the orthogonal complement of W. And more than that, here is the way in which the vector u could be found. This is called so this vector u has a name, it's called the orthogonal projection of the vector y on the subspace W. And I was telling you that the simplest image to have in mind is something like R3, which with the xy plane inside and the orthogonal complement, which is the z-axis. Right, so if this would be W, then the z-axis would become the orthogonal complement, because those would be vectors that are perpendicular to anything in the plane, in the xy plane. And then if you have a vector, an arbitrary vector v would of course stand for the y in the theorem there, then you know that you can drop the perpendicular, right, onto the xy plane and z-axis. It doesn't look very good what I did here, but anyways, you can create that kind of rectangle there with v as a diagonal, and in this way this projection here would be u, and this vector here would be what we call z. It's a different z than the z-axis. So it makes sense to call it the orthogonal projection, and the very first thing that we'll prove today is that this vector u, the orthogonal projection, is closest to the original vector y in W, and if you look at the picture, it makes sense. It's the closest vector in the xy plane to the vector v in there in the picture. So let's try to prove this. So let y be a vector in V. Y, according to the theorem above, can be written in a unique way as u plus z, where u is in W and z is in W perp. And let x be another vector in W. What we have to show is that for any x in W, this inequality here holds. All right, so x is a vector in W. I want to show that the norm of y minus x is greater than or equal than the norm of y minus u. Okay, so let's start with a norm of y minus u. Well, y is u plus z. That's basically just the norm of z. On the other hand, the norm of y minus x is the norm of u plus z minus x, which I want to regroup like this. U minus x plus z. Now, why would I do that? Because both u and x are vectors in W, right? X is in W, u is in W. So u minus x is a vector in W, and z is in W per. All right, so here's what I'm going to do. I'm going to put squares everywhere, even in the equation above. And I'm going to use a property next, which is something that I don't know if you took a look at the homework that is due next week, but it's part of that homework. So part of that homework for two arbitrary vectors, let's use other letters like V1 and V2. So in an inner product space, if V1 and V2 are two vectors that are orthogonal to each other, so the inner product is 0, then the norm of V1 plus V2 squared is the norm of V1 squared plus the norm of V2 squared. So that, again, this is a homework problem, so I'm not going to go into the proof, but just to have some visual interpretation of this, that is all you need. Two vectors are orthogonal, so they are perpendicular to each other. If you form a right triangle there, right, then what's going to happen? You know, you have that, you have the theorem, right, Pythagoras theorem and so on. So visually it makes sense. Then you have to go ahead and prove it, and you're going to, the proof is quite straightforward. If you just express the norm squared as the inner product between each vector and itself, and then expand on that inner product, is going to be immediate. So anyways, going back to the norm of y minus x squared, so we expressed it as the norm of u minus x plus z. U minus x is in W, z is in the orthogonal complement, so they are perpendicular to each other, right? Z and u minus x. So the norm of this squared is the norm of u minus x squared plus the norm of z squared. All right, so this is what we had to prove. We're going to prove it with the squares on. It doesn't matter. The norm is greater than or equal than 0, so I can easily take the square root afterwards, right? So I'll prove the inequality with squares. This is the left side. And this is the right-hand side. So the left side, which is supposed to be greater, right, is the norm of z squared plus something non-negative. The right side is just the norm of z squared, so it's automatically satisfied. All right, so we proved the inequality, and furthermore, when can we get equality? Well, to have those two things equal to each other in the end, that would mean that this additional term, the norm of u minus x squared, would have to be 0. But the norm of a vector is 0 only when that's the 0 vector. So when x equals the orthogonal projection. So it is the only one that is closest to the original vector y. Okay. So what I want to do next is to actually compute, numerically an orthogonal projection. Let me get some space here. For example, the inner product space is V. Polynomials of degree at most 3 with real coefficients, with the inner product defined like this. Integral from -1 to 1 f of t times g of t dt. Find the orthogonal projection of the vector. It's going to be a polynomial, right? The vector. So the polynomial x cubed, right? X cubed is a polynomial in P sub 3 of R. Find the orthogonal projection of this on P sub 2 of R. Now clearly polynomials of degree at most 2 would represent the subspace of the polynomials of degree at most 3, right? Because it's closed under addition, under scalar multiplication. If you add 2 polynomials of degree at most 2, you still get a polynomial of degree at most 2 and so on. So let's find the orthogonal projection of this polynomial onto P sub 2 of R. All right, so let me go back to the theorem. What is it that I need? Well, I need to break that x cubed into a sum, u plus z. And I know exactly how to find u, right? I have a formula for u. The formula, though, is based on an orthonormal basis for w, right? Who is w for us? P sub 2 of R, right? So in order to start this process going, I'm going to need an orthonormal basis for P sub 2 of R. Now, how do we get such a thing? How do we find an orthonormal basis for P sub 2 of R? Going to be in that ugly, messy way, right? It's the Gram-Schmidt. So we're going to have to start with a basis for P sub 2 of R. We'll just pick the standard basis, 1x x squared. And apply Gram-Schmidt orthogonal basis. So we've seen an example like this before. I'm not going to waste more time on, applying the Gram-Schmidt again. Hopefully it's clear how to apply that thing. Let me tell you what you get. Say alpha prime. Note that the first 2 vectors are unchanged. Why is that? In the Gram-Schmidt, the first vector is always transferred, right? So 1 should be there, but why is x the second vector? Well, as long as the first and the second vector are orthogonal to each other, Gram-Schmidt doesn't do anything, right? Because it's an orthogonalization process. If they're already orthogonal, you're fine. So why are they orthogonal to each other? Well, if you compute the inner product between 1 and x as the integral from -1 to 1 of 1 times g of t, so t, dt. The integral of t is t squared over 2 evaluated from -1 to 1, you're going to get 0. Or if you want, t is just an odd function, right? Going from -1 to 1, the integral will always be 0. All right, so we got an orthogonal basis. That's not all we need. We need an orthonormal basis. So we're going to need to divide each vector by its norm, right? The norm of 1, for instance, would be the inner product between 1 and 1. So we need to compute all those integrals. Again, I have them here. So here it is. Now the cube root is 3 times square root 5/8. All right, so we got an orthonormal basis. So now we're ready to make that theorem work, right? So let me go back to the theorem. So the theorem said, so now I have my orthonormal basis v1, v2, v3. Then u is the sum of yvi times vi. So v1, v2, v3. So the orthogonal projection of x cubed on p sub 2 of r is u, which is, so it was the sum of y vi, inner product, times vi. Y is x cubed. So x cubed v1, inner product, times v1, plus x cubed v2, times v2, plus x cubed v3, times v3. I kind of got away without computing anything, so let's at least compute this final step here. So what is the inner product between x cubed and v1? Inner product between x cubed and v1 is the integral from -1 to 1 f of t, so t cubed, times v1 is a function of t, but v1 is just constant, equal to 1 over the square root of 2 dt. So t to the 4th over 4 square root of 2 between -1 and 1. Again, t cubed is in fact an odd function. The integral will end up being 0 from -1 to 1. All right, so that's nice. The first part is 0. The second one, x cubed v2, integral from -1 to 1, t cubed times the square root of 3/2 times t dt. So it's the integral of t to the 4th, t to the 5th over 5, evaluated from -1 to 1, which will end up being 2 over 5 times square root of 3 over 2. So square root of 3 over 2 times 2 over 5 times v2, which is another square root of 3 over 2 times x, right? All right, and finally, x cubed inner product with v3, integral from -1 to 1, t cubed. v3 is 3 square root of 5 over 8, t squared minus 1/3. dt. And if you exclude the scalars here, you're going to see that it's in fact t to the fifth minus t to the third in there. So it's a polynomial where all the degrees are odd. So again, the integral from -1 to 1 will end up being 0. All right, so in the end, we get 3/2 times 2/5, so 3/5 x as the orthogonal projection of x cubed. So quite computational, but nothing very complicated, I would say. Okay. So the final idea in this section is relating this idea of orthogonal complement to somehow to direct sums, if you want, or to dimensions. So let's look into this. So we start with an orthonormal set S in a finite dimensional inner product space. And first, we want to see that we can extend S to an orthonormal basis for V. Remember from a while ago that any basis for a subspace could be extended to a basis for the whole space, but this is saying even more that if you have an orthonormal basis for a subspace, you can extend that to an orthonormal basis for the big space. Okay. Why is that? Well, because S is an orthonormal set. It is in particular orthogonal, right? Which we know that implies it is linearly independent. Okay, so we have a linearly independent set of k vectors, and we know that from basic theory of vector spaces that it can be extended to a basis for the whole space. But the question that remains here is, why would this basis be orthonormal still? Let's call it beta. Well, all right, so we can control the first k entries, right? They were orthonormal to start with, but the remaining n minus k vectors, we have no control over them, right? What we can still do is to take this set beta and apply Gram-Schmidt to it, right? And turn that into an orthogonal set, at least. All right. So let's apply Gram-Schmidt. Let me change the names here because it looks like I got the set that I needed and I haven't yet. All right, so I'm adding n minus k vectors. Let me call them v prime k plus 1 up to v prime k. Let's see what we get when we apply Gram-Schmidt. So remember, Gram-Schmidt takes the first vector as it is. My first vector is v1, right? Then the second vector, v2, well, that is already orthogonal to v1 because they were part of the set, the original set S, which was orthonormal to start with. So Gram-Schmidt will not change that, right? It doesn't change vectors that are already orthogonal. And It's going to actually leave the first k vectors unchanged. They were all orthogonal to each other. They form an orthogonal set. It's going to maybe change the remaining n minus k vectors. Again, we had no control over those. They might or might not be orthogonal. So we'll change those. Let's say double prime. And now it is an orthogonal basis. Well, I need it to be orthonormal, right? More than that. So I need to normalize each vector. But again, the first k were part of an orthonormal set, so I have nothing to do there. They all have norm 1. So maybe all that I need to do is to normalize each of the remaining n minus k vectors, right? So divide each of the last n minus k vectors by their norms. And we get an orthonormal basis. And now after normalizing, let's just call them vk plus 1 up to vn. Okay, so we started with an orthonormal set, v1 through vk, and we extended it to an orthonormal basis. So we're done with part A. Part B. So we call W the span of S, so the span of the set v1 through vk. We want to show that the remaining n minus k vectors form an orthonormal basis for W perp. Well, first of all, let's see, are they vectors in W perp? Well, to be vectors in there, that would mean they have to be orthogonal to everything in W, right? So is it true that they are orthogonal to everything in W? Vj, what is something in W? What does something in W look like? Well, W was the span of V1 through Vk, right? So something in W looks like the sum of Ai, Vi, I going from 1 to k. That is an arbitrary element of W. We can pull those scalars out in complex conjugate if necessary. So now what's this inner product? Inner product between Vj and Vi. J, remember, is greater than k plus 1. I is between 1 and k. The vectors were orthogonal, so it's just going to be 0 each of them. Okay, so every Vj is part of W perp, but that doesn't necessarily mean that the set forms an orthonormal basis, right, for W perp. It forms an independent, linearly independent set. It's an orthogonal set in there. So all there is to show now is that W perp is in fact the span. So it needs to be generating now. That's the only thing left. So let X be a vector in W perp. I want to write it as a linear combination of V sub k plus 1 up to Vn, right? Well, first of all, because this one here was a basis for the entire space V, I can write X as a linear combination of all those vectors, right? Between 1 and n. But remember that when I do this, because the set is orthonormal, we have a very nice way to write down those coefficients of the linear combination. They are just the inner products between X and each vector. So this will be inner product between X and Vi times Di. I equals 1 to n. Okay, but if I look inside this sum from 1 to n, and I concentrate on the first k terms, so the inner product between x and v1 up to the inner product between x and vk, they will all be 0. Why is that? Because x is in W perp, so it's orthogonal to anything coming from V1 through Vk. So the inner product between x and V1 is 0, x and V2 is 0, x and Vk is 0. So this is in fact the same as the sum from k plus 1 to n. So I'm using some coefficients and only the vectors from k plus 1 to n. But that's precisely what I need, the span of this set. Okay. And finally, again, if you think about that R3 idea, right, we have the xy plane, dimension 2, the z-axis, dimension 1, the sum ends up being 3, right, which is the dimension of R3, so it makes sense. Well, if you look back at part B, and the setting that we have here, so W is the span of S, so what dimension does W have? Okay. And then S1 is an orthonormal basis for W perp. What dimension does W perp have? What dimension does it have? It's going to be n minus k. N minus k. N minus k plus k. Oh, and by the way, I can just add them up. Why can I add them up? There is no overlap, right? There will never be an overlap between W and W perp. We've seen that before, unless it's the 0 vector, right? So now n minus k plus k gives you, of course, n. And that's exactly what part C claims to have. Oh. So this is the end of 6.2. Any questions? So the most important thing here to remember would definitely be the existence of Gram-Schmidt, not the Gram-Schmidt by itself. So if you ever need it, you can just ask for it on a test. You don't have to memorize that thing, right? Anyways, on a test, I will try to just give you what you need, so you don't have to waste time going through Gram-Schmidt. So if you need an orthonormal basis for a space, just ask for it and can provide it if it's relevant to the question, let's say. Okay, let's move on. Pretty important idea in general in matrix theory and operator theory is the notion of the adjoint of a linear operator. What does this mean? You have a linear operator, so a linear transformation from a vector space V to itself. The vector space is equipped with an inner product, so V is an inner product space. So it has an orthonormal basis, right? Let's say beta. All right. To the matrix T, we can associate, to the transformation T, we can associate a matrix, the matrix of T in the basis beta. Beta being the orthonormal, the nice orthonormal basis. Okay. But every matrix has an adjoint, right? In matrix theory, there is this notion of the adjoint that we're trying to get into the linear transformation or operator theory in the sense, is there a linear transformation from V to V whose matrix in the basis beta is the adjoint of the original matrix? That makes sense? So I need a transformation from V to V. I'm not going to call it question mark. It will have a name. T star, right? Just the most natural thing. So T star will be a linear operator again on V, whose matrix in that basis beta is just the adjoint of the original matrix of T, right? To complete this kind of picture. So the existence of this thing and the way to define it is what we'll be dealing with. So before we start this process, let's just make one remark. So let's say V is an inner product space. Let's say x0 is fixed in V. And define G from V into F as G of x equals the inner product between x and that fixed x0. Right? It's clearly taking a vector in V into a scalar, right? Because the inner product gives you a scalar in F. And more than that, this is a linear transformation. Why is it linear? Well, it's linear because the inner product is linear in the first variable. Okay, so what have we seen? We've seen that this kind of transformation from V to F is linear. So what? Well, it turns out that any linear transformation from V to F has to look like that. So has to be. So if you start with a linear transformation from V to F, right? So define on the space with values in the scalar, then G must be the inner product between x and some unique fixed vector y, which we called x0 above, in the property above. And this will turn out to be essential in the definition of the adjoint of a linear operator. Let's see why. Okay, so V is a finite dimensional inner product space, so it has an orthonormal basis beta. Okay, so we must show that there exists a unique vector y. Uniqueness, we'll deal with it at the end, right? We'll deal first with existence. It's not going to be a very nice existence. We'll just come out with a vector. So let y be the following vector. Sum I equals 1 to n. G of vi conjugate times vi. Why conjugate? Because y, if you look above here, appears in the second argument of the inner product, right? So when you simplify things, you want to pull the scalars out, you need another complex conjugate on top. So that's why you need g of vi conjugate. Okay, so then the inner product between, well, how do we put this? Let me put it like this. Let h of x be the inner product between x and this y that we defined above. Show that this function and the one above, g, are one and the same. Now, how do you show that two functions are equal? Well, they have to agree at every vector, right? But isn't it enough to show that they agree at every vector in a basis? Because if they agree on a basis, then they will, and they are linear, you can extend that to any linear combination, right? So it's enough to show that h of vi, or vj, let's say, equals g of vj for every j. Okay, so what is h of vj? H of vj is the sum, there is no sum yet, is the inner product between vj and y. So is the inner product between vj and the sum I equals 1 to n g of vi conjugate times vi. And in the second argument, the inner product will pull the scalars out with a conjugate and will preserve linearity. So this is the sum I equals 1 to n g of vi times the inner product between vj and vi. But now the inner product between vj and vi is 0 unless I and j are equal, right? In which case it is 1 because that basis was orthonormal. When I equals j, we just end up with g of vj. And that is exactly what we wanted. That h and g agree on a basis, so they agree everywhere. Okay. Almost done. Except that we came up with a vector y, and that needs to be unique. So what if there exists another vector y prime in V such that g of x is the inner product between x and y prime as well. And it was also the inner product between x and y. How can that be? Well, we showed that when you have an identity, an equality like this, that holds for every x in V, it was one of the properties of the inner product, then that will imply that y and y prime must be equal. And that's something from 6.1, one of the properties there. Okay. So again, this is just a technical result. So we proved that any linear transformation from V into the scalars must look like that, the inner product between x and the fixed unique vector. All right, so let's go to the main result. So you have a finite dimensional inner product space, and that turns out to be essential. T is a linear operator on V. Then there exists a unique function that turns out to be linear, right? So a unique linear transformation called T star from V to V with this very nice property here. So basically, what the star does is you can move it from one argument of the inner product into the second argument, right? By putting the star there. So you leave x by itself and move t over y with a star, right? It just moves from left to right, and that's pretty nice what happens there. Let's see how this works. So let y be an element of V. Define G from V to F. I want to connect it to the previous result. By G of x equals the inner product between T of x and y. Okay, so I have this map from V to F, but I want it to be a linear transformation in order for the previous result to apply. So let's see, G of Cx1 plus x2 is the inner product between T of Cx1 plus x2 and y. T was a linear transformation, right? So T of Cx1 plus x2 is C T of x1 plus T of x2. Inner product with y. Inner product linear in the first argument. So this is C, inner product between T of x1 and y, plus inner product between T of x2 and y. And that's nothing more than C times G of x1 plus G of x2. Okay, so we have a linear operator, or linear, no, not an operator, sorry, a linear transformation from V into F. Defined how it is, but once we have a linear transformation from V to F, the previous result says that it must look like that, right? The inner product between X and something. Okay, so theorem above, which is called what? 6.8. A fixed y, I cannot use y anymore because I used it above. Let me call it y prime. For some unique y prime in V. So let me rewrite this. So G was the inner product between T of x and y. And now it equals the inner product between x and y prime. And that holds for every x. If you look at what we have to show, it becomes pretty clear what T star should be defined to be, right? So we define T star of y to be that y prime. Right, so for every y, we found a unique y prime, so that's a perfectly well-defined function from V into V. So T of y equals y prime. T star of y equals y prime. T star from V into V. So what else is there to show? Well, it cannot be just any function or any kind of mapping. It has to be a linear one. So let's show that. Okay, so I need to show that T star of a y1 plus y2 equals a T star of y1 plus T star of y2, where y1, y2 are vectors, a is a scalar. Okay, now you realize that this whole process is so technical and obscure, right? It doesn't really tell you anything about what T star should be, and that's going to make things even more difficult in examples and applications of computing T star of an actual vector. But it's still difficult here, right? So the only way in which I know how to deal with T star is through this identity, basically, right? So this identity, which in the end we called y prime T star of y. That's the only thing that we have to control, maybe T star. Okay, so I'm going to start with inner product between x and T star of a y1 plus y2. All right, so this underlined identity here, this one here, tells us that T can move back into the first argument, right, of the inner product. So this is the same as T of x, inner product with a y1 plus y2. Which we know how to deal with a linear combination in the second argument. It will just pull the scalars in complex conjugates. So this is a bar, T of x inner product with y1 plus T of x inner product with y2. And now I'm going to move everything back into the second argument. So in the first inner product, I'll take T and move it into T star over y1. So this is a bar, inner product between x and T star of y1. And the second inner product is the inner product between x and T star of y2. And now build everything back together. So move a bar into the second argument as an a and use linearity to get a T star of y1 plus T star of y2. So we started here. We ended up with this, and x is completely arbitrary. Whenever the inner product between x and the vector equals the inner product between x and another vector for every x, then the two vectors on the right must be equal. Again, that property from 6.1. So T star is linear. Okay? One more thing, though, that I missed. There is no other like it, right? It's the only one that has this property. Okay? So let's just assume that there is another one. Let's call it U. It's going from V to V. And it has the property that, well, the same property that T star has. The inner product between T of x and y is the inner product between x and U of y, right? For any two vectors, x and y. But T of x inner product with y is the same as x T star of y. And we get back to that same property from 6.1, right? Whenever that holds for every x, it can only happen if the right sides are equal. And we are done. So the adjoint is unique. So a unique function that has this nice property here that can be moved around. So before we go to an example, I just want to point out another thing. So through this theorem, all we know is that t can move from the first argument into the second with a star. It's still true that you can do it backwards. If it's in the second argument, it can move into the first with a star. So let's look into that. So let's say note. So I want to do, so we had t of x comma y is x, t of x comma t star of y. So now I'm going to do this. And I want to move t with a star in the first argument. Okay. So I don't know how to deal with t star if t is in the second argument, but I know how to use that property if t is in the first argument. So I'll switch positions by taking the complex conjugate. So this is the complex conjugate of t of y comma x. Okay, but now t could be moved in the second argument as the adjoint. So that's the complex conjugate of the inner product between y and t star of x. And now I'm going to switch them back, right? And that's exactly what I want, right? So I can, not only that I can move t from the first into the second with the adjoint, I can do it backwards, from the second into the first. It's still moved with the adjoint. One more thing, again, before the example. I said that it's essential that V is a finite dimensional vector space. Not that the arguments that I had here would not work in case T star existed, but existence might not be the case anymore. So on an infinite dimensional vector space, not all linear transformations have adjoints. And we'll look into an example later on with a transformation infinite dimensional space without adjoints. So you can still define it in the same way. The properties would be the same as far as if T star would exist. Okay. I have here. No. So let's look at some examples. (3a) on page 366. V is R2. T is a linear operator on R2. It takes a pair AB into the pair 2A plus B, A minus 3B. R2 is seen here as an inner product space with the standard inner product, right? The sum of xi, yi conjugate, but there is no conjugate because everything is real. So it's just the sum of xi, yi, right? Fine. T star of the pair 3, 5. To compute the value of the adjoint of a given vector in there, like 3, 5. So again, that proof before doesn't really give you anything, right? It's just, we just showed that something exists that is unique without seeing it, right? So how do we actually see it now? Well, as I said, all that matters is this highlighted identity there. That T of x inner product with y is x T star of y. That's the thing that you always use to figure out what T star is. All right, but I need to find T star of that pair 3, 5, I think it was. Yeah, I need to find T star of 3, 5. So that means y should be 3, 5, right? What is x? Well, I don't know. It needs to hold for every x. So I'll just let x be arbitrary. So I need to start with the inner product between t of x and the pair 3, 5. Let's look at that. Right, so now t star of 3, 5 shows up there on the right. And this will hold for every x in R2. So let's just say that x is AB, the pair AB, right? It has to be a pair in R2. Okay, so what is t of x then? Well, it's t of AB, so that's the pair 2a plus b, comma a minus 3b, right? That's t of x, and we need the inner product between that and the pair 3, 5. That's the left side, right, of the identity defining t star of 3, 5. And this inner product we can compute, right? Again, is the standard inner product, so I just do 3 times 2a plus b plus 5 times a minus 3b. So what is it? 6a plus 5a, so 11a plus 3b minus 15b. So 11a minus 12b. Right? That's the left side. Let's look at the right side. What do we have there on the right side? On the right side, we have the inner product between x, which is the pair AB, right? And this thing that we need to find. This, we don't know what it is. But the inner product between those two things should be equal to what? Well, it should be equal to 11a minus 12b. Which, isn't it the inner product between AB and 11 and negative 12? That's how you get 11a minus 12b, right? By taking the inner product between AB and 11 negative 12. And remember, this should hold for any a and b. So for any vector in the first argument, when is that possible? Only when the second arguments are equal to each other. Okay. No. So if things are computational like this, no. In general, I mean, not in general, but mathematically speaking, that's not the importance of T star. There are a lot of nice properties that you can build on that identity there, and you work with it in more abstract setting without knowing the exact numerical value. Exactly, and with which properties it has, but for this kind of course, we're also interested in how do we actually compute it, what is it. Okay. But later on, if you need this, you're not going to care about the actual numerical values. So what I want to say is that this was a pretty easy example, just like a warm-up, so I want to give you another one. And let's see what you think about that one. So let's do 3C on the same page. The vector space, the inner product space is P1 of R. It is an inner product again with that, it's an inner product space with that inner product, the integral from -1 to 1, f of t, g of t. And T is a linear transform, linear operator on V. Defined by T of F equals F prime plus 3F. T of F I meant here. T of F is F prime plus 3F. Find T star of the following vector. The function 4 minus 2t. We have 10 minutes left. We probably won't get to do anything else, so I'll let you think for a couple of minutes and see in which direction you would go with this.
First we would do that part of T of X and 4 minus 2.
So T of X would be T of F. No, anyways, T of F, inner product with 4 minus 2t. And this would be the same as inner product between F, which is in fact an F of X, right? And T star of 4 minus 2t.
Then we integrate from -1 to 1.
Mm-hmm.
Get that.
Okay, so on the left side you have the integral from -1 to 1 of T of F as a function of t times 4 minus 2t dt. But in order to integrate, I need to know something about that function. I mean, I cannot just integrate now. So
Prime plus 3F.
it is f prime plus 3f, but still doesn't say too much. But where do these functions belong? They are not just anything. Basis of what? Of P1? Yes, but it must hold for any f, that identity. If you want to go down to that, it's still possible, but you're not going to have the identity written in full generality if you want. So the thing is that it's P1. How hard is P1, right? P1 is just a linear transformation. It's a linear map, right? So it's AX plus B. If you want, you can just apply it for X separately and for 1 separately. If I want to put everything together, I'll just call it AX plus B. So and then I can just say that A and B are completely arbitrary, right, in my space, which is R. Okay. So what would T of F be? It's the derivative, which is A, plus 3 times F. So 3ax, right, written again as a linear function, it's 3ax plus 3b plus a. Okay, so this is 3at plus 3b plus a. Now we can figure out what that integral is. Let's see what it is. So integral from -1 to 1. So 3at plus 3b plus a is multiplied by 4 minus 2t, right? So you're going to get a second degree polynomial out of that. Which is this one. I'm still working on the left side, right, of the initial identity, which was this one. All right, now, the part with t doesn't matter. Why not? Because I integrate from -1 to 1, right? T is odd, it will turn into t squared over 2, it will give you 0. As the integral will be 0, right? Of the thing in the middle, I mean. This one here will not matter, the part with t, containing t. Through integration, it will not matter. So that leaves you with those two things to integrate. So the first one is what? -2a t cubed, evaluated from -1 to 1. Again, the second part we said it's 0. And the third part is 4 times 3b plus a times t from -1 to 1. So -2a times what? Times 1 minus -1, so times 2. -4a. Value of 1 at 1 minus the value of -1 will give you 8 times 3b plus a. So overall I get 4a plus 24b. Remember that a and b are arbitrary. Okay. So now what do you do? That was the left side, right? To get the right side to look like that, right? But how? Because it's through integration, right? How to get it to look like that? One way would be to just say, okay, so this is what I need to find, right? But t star goes from p1 to p1, so t star of 4 minus 2t is also some first degree polynomial like c t plus d. Right? I need to figure out what c and d are. So what is the inner product between f of x and c t plus d? Well, it's cx plus d, but it doesn't matter. F of x was ax plus b, right? So integral from -1 to 1, at plus b times ct plus d dt. So integral from -1 to 1, ac t squared plus t times ad plus bc plus bd. Again, the term with t will give you 0. AC t cubed over 3 from -1 to 1 will give you 2/3. And BD times t will give you 2BD. This should equal 4A plus 24B, we said, right? For any A and B. So what are C and D that would make this happen? If you want, you can put it like this. This should hold for any two A and B. The only way for this to happen is when C is 6 and D is 12. So in conclusion, T star of 4 minus 2T is what? 6T plus 12. The conclusion is do whatever you have to do to find those numbers. All right, so I'll stop here. I'll see you on Monday. So the homework is posted and is due on Monday.